engineer from PyTorch Distributed. Today, Iris, and then Xilun, we're going to talk about Tensor Parallel, 2D Parallel, and also our update on the PyTorch scalability efforts that we've been working on during the past 6 to 9 months. Yeah. So first of all, when we look at the diagram from the how the model size scales, it kind of go up crazily. So for example, GPT-2 only have 1.5 billion parameters, but GPT-3 have 175 billion parameters, right? And also the data size also increase hugely. For example, for Llama V2, we're using 2 trillion tokens to train the model, right? And also what's more is that we are using way more GPUs now to train a LLM, like 2K, 4K, even 16K, anything above that. So that brings some challenges and some composable requirements to us. So for the, for large language models, originally we have this kind of data parallel training, right? Like DDP, so distributed data parallel. So that's simple. You copy the model, multiple replicas, and then you send different data to each GPUs. But this won't work when the model becomes so big that the model cannot fit in the memory of one single GPUs. Then we have FSDP that we shard the weight across all GPUs or even across hosts. And then during the forward and backward, we call all gather. We get all the weight, and then we do the forward and backward. But the thing is that when it comes to super large scale, the communication across hosts becomes like a bottleneck for FSDP. So the trick for FSDP is that although you'll call all gather, but we kind of hide the communication with basically we overlap it with computation so that the all gather cost is like a free lunch, right? But with the super large scale, the all gather becomes super long, and then it's completely compound. Then there's nothing you can hide it. So then when we then have hybrid sharded data parallel, and also we have tensor parallel, sequence parallel, and then pipeline parallel. So for tensor parallel and sequence parallel, instead of we still shard the weight, but instead of call all gather the model parameters, we now do some all gather or all reduce for the activations. And for pipeline parallel, this will reduce the communication cost a lot because there's only point-to-point communication. And of course, Megatron is having this 3D parallel already. So I'm gonna also talk about our native solution in the next slide. But this comes with some challenge for us is that all these solutions, like PyTorch native solutions, are kind of built individually. And then when we first start to build them, we don't think of composability. So that's why we see some composable issues between each of these training paradigms. And also, when it comes to like I said, 2D, 3D parallelism, the static and then the process group management becomes a very complicated. I think Iris is going to talk about how we kind of handle this static and then checkpointing in a more uniform way. Last but not least, a lot of those kind of communication and computation optimization and overlapping right now are kind of hand-tuned. For example, FSDP has its prefetching logic, so DDP has its bucketizing logic, and then Tensor Parallel has its own a trick there. But when we combine them together, there are way more optimization space for us. So we want to leverage new technique, for example, PyTorch compile to further optimize the in the case of 2D and 3D parallelism. Okay, all right. So during the past 6 to 9 months, we implement the tensor parallel based on top of the distributed tensor last year, and then when we had a prototyping for FSDP plus TP, so that's why we call it 2D parallel. And then we now had the DDP working with TP as well. For forward and backward. And also we also had a prototyping for pipeline parallelism working with tensor parallel together. And then we're right now working on 3D parallel also. Another thing is that when we apply tensor parallel on transformer model, we see some UX pain points, some like API are not very good for user to use. So we made some changes to the tensor parallel APIs. So now they're all available in PyTorch nightly build. So feel free to try it out and let us know how that goes. And the third thing is that we have this activation checkpointing wrapper for tensor parallel. So activation checkpointing is that because activation size is so big, so we just throw them away in the forward, and then in the backward, we just recompute the forward again, and then do the backward. That's activation checkpointing. And then for tensor parallel, because the input are the same across all the tensor parallel ranks, then we somehow just shard the input as well, and then all gather in the in the backward again. Yeah. So last but not least, we're now working on enabling distributed inference for large language model using native PyTorch tensor parallelism. Another thing we're having that available in the nightly build is sequence parallel. Like I mentioned, in tensor parallel, all the input are the same across all TP ranks. But for this one, instead of sending same exact input across all TP ranks, we shard across sequence dimension, so that we first need to call one altogether across, like to gather all the input together. Then it's like a very classical Megatron style two linear layer, and then in the end we call one reduce scatter. The tensor becomes back to its original shape. And then the way it works is that when you first have a column-wise sharding and then you have a row-wise sharding, in the end, in the middle, there's no need to call any like collective, and then you just need to either in the scenario of tensor parallel case, you just call one or reduce, or in the scenario of sequence parallel, we call a reduce scatter, and then after reduce scatter, you can call layer norm or softmax, which is in the last dimension. They're all fine, and then when it comes to like a next module, then we'll repeat this. This all gather, reduce, scatter pair thing again. So that's we already have enabled it for sequence parallel in nightly build. Okay, another thing I want to mention here is that we have noticed some like performance gap in distributed tensor, and also have some new features for distributed tensor. So for performance, because distributed tensor is using tensor subclass, so it comes with some like CPU overhead. So we try to reduce the CPU overhead as much as possible. This is gonna benefit both small models and an inference, because for large models, its CPU overhead can be well hidden by like FSCP, and also, because it's mostly CPU bound, right? So then all these CPU costs can be well hidden. But for small models and inference, we need to reduce the CPU overhead as much as possible. And also, like I mentioned, we are integrating tensor parallel with torch compile. That torch compile can help us further do some reordering and then scheduling to better overlap the computation and communication. Last but not least, we enable random generators op. Like for example, for dropout on a replicate tensor across like different ranks, we want them to have exact result across all ranks. So just give you an example. All this gonna like random or some distribution, this op will have correct behaviors on both sharded and replicate DTensor. All right. So next, I'm going to hand over to Iris to talk about distributed tensor and then all the static and the checkpointing stuff.
Yeah. So thanks, Junjie, for going over like all the challenges for composable distributed training and sharing updates to our features. Now I want to go into our UX for trainer initialization as well as like a backend powering our Tensor Parallel APIs. So to better support like composable distributed training initialization, we're introducing DeviceMesh. So DeviceMesh is a higher level abstraction that manages process group. It allows the user to easily create internal and intra-node process group without worrying about too much about how to set up the ranks correctly and how to manage sub-process group as well. So we can see from the example from the bottom left, if you want to set up like 2 hosts with 2 devices each host, we can simply create a 2D mesh that connects devices within each host, and it also would connect each device with its counterpart inside the other host in a homogeneous setup. So why is device mesh useful? So because for multi-dimensional parallelism, right, in 2D, 3D settings, we need to set up the Nico communicator to correctly before applying any sort of parallelism. For example, here is an example of like how distributed developer could be manually creating process group for a 2D hybrid sharding. As you can see, it's fairly complicated and very error prone. And with device mesh, things can become so much easier. And we can see that user just need to tell init device mesh on the right-hand side the number of CUDA device per host, and the device mesh will automatically set up like Nico communicators within each host and across hosts. So it really like it becomes like into 2 lines. It's also important to note that like after creation of device mesh, user can still get access to the underlying process group if needed. This significantly simplifies the setup of like a multi-dimensional parallelism. And next, I want to get into like DET Tensor for a little bit more. So which DET Tensor is like the backend powering our PyTorch native Tensor Parallel APIs. So DET Tensor is our new like fundamental abstraction that performs tensor level sharding computations. So it brings a lot of like a composability advantage. First, it provides a uniform tensor sharding layout to represent different parallelism and their static, right? And secondly, it also allows user to perform sharded computation easily in an SPMD style. So without needing to worry actually needing to write backward formula for collectives and potentially hitting the risk of deadlock with some manual collectives. So DET Tensor so here you can see like DET Tensor allows sharding on a tensor dimension over a set of devices and replication over a set of devices. It automatically partitions the data to sharded or replicated or even more complicating sharding strategy according to the device mesh and placement user define. So for example, you can create a sharded DET Tensor that only sharded on a set of devices and replicate on the rest of devices by just specifying a 2D device mesh and the corresponding placement. So in the third diagram, so you would specify shard and replicate on different mesh dimension. So with device mesh and DET Tensor as like the fundamental building block, we can make large model training much easier. So Junjie went through earlier that we have our 2D solutions, and a couple pain points that we have seen in the past for Tensor Parallel is usually Tensor Parallel is like intrusive to the model call. And so when like the distributed code is intertwined with training call, it really increases your maintenance burden, right? And another pain point is like composition makes checkpointing hard as well. So for our native 2D APIs, other than having like the competitive end-to-end performance, we're also looking to solve the pain points that I just mentioned. So we can see from this code example that device management can be easily achieved by creating a 2D device mesh with the zeroth dimension of device mesh performing data parallel and the first dimension performing tensor parallel. And as you can see, you can easily slice this 2D device mesh into 1D device mesh with annotation telling which dimension of device mesh the parallelism should be using. And to apply tensor parallel to your model, you can specify parallelized plan for the transformer block by composing column-wise parallel, row-wise parallel style together, and apply them each layer of the transformer and adjusting the number of your head, the head. So by applying parallelism outside of the model code, user can really minimize the code change to LLM to allow efficient tensor parallel plus data parallel solution. Before going into our checkpointing solution, I want to quickly talk about what makes checkpointing hard in distributed settings, right? Checkpointing would not be hard if you always load with the same parallelism solution and same row size. You can simply set up the same number of trainer every time, and you directly use torch.save and torch.load without worrying too much about anything. But however, in reality, that's not the case. As in distributed, there are different scenarios where you need to do data shuffling. We call loading the safe tensor into like a different parallelism or different row size resharding. So for example, resharding is needed when you say you're moving from training to inference. Say if you want to do 2D training in a large row size, and later you might only want to do inference with tensor parallel only in a smaller row size, you would need resharding. And also from offline training to online training, which requires both resharding the model and optimize the states. And also you can see from pre-training and fine-tuning, you need to reshard like the model as well. So for that, we have a PyTorch native checkpoint solution, distributed checkpoint. This is beta ready in PyTorch 2.1, and together with DET Tensor, we're aiming to help users to solve the pain points for checkpointing under distributed settings. So distributed checkpoint supports efficient sharded static safe and low for fully sharded data parallel and tensor parallel. It avoids writing redundant copy to disk and allow parallels read and write. Also supports checkpoint load time resharding to like different row size when the cluster environment changes. And furthermore, like with this uniform static that contains DET Tensor, distributed checkpoint allow user to save in one type of parallelism and load into another type of parallelism very seamlessly. So you can checkpoint in a 2D parallel setting for pre-training and later easily load it back using 1D parallelism for fine-tuning or inference. And next I'll pass it to Xilun to talk about control plane.
Thanks, Aris. So my name is Xilun. I'm also from PyTorch Distributed. And my focus is on the communication backend of PyTorch. So the communication backend of PyTorch has proven to be stable and reliable in the modern distributed training jobs. So by modern distributed training jobs, I mean like 64 GPUs, DDP, FSDP. But recently, we have the example of Llama, which takes 2K GPUs to train, right? Which is crazy. So we have seen this trend. We are using more and more GPUs, and this put the pressure on the or question mark on the communication backend. Is it okay, or is it still reliable for that number? So this initiates our effort to benchmark the communication backend at this super large scale. By super large scale, I mean like 4K, 8K, even 16K, 24K. So these numbers might be crazy right now, but I think it will not be that rare in the following like 5 years. So for the communication backend, there are two critical components. The first is called TCPStore,
and the second is called ProcessGroup, and Gloo is one of the backend of ProcessGroup. You can implement your own backend for your custom device hardware. So ProcessGroup is a abstraction layer above the actual communication. We use PG to represent collectives performed on like a certain number of GPUs or ranks. So the Gloo is the library for PG on CPU. So it can be used for like distributed checkpointing. It can be used for like metadata, communication. So it's mainly for the data on the host. And we also have Nickel as the backend for GPU, which is responsible for the data on the device. And the TCPStore is a key value store. It is centralized, usually hosted on the first rank 0, and it is responsible for exchanging the data, which don't fall into the categories I mentioned above. So this is the roles of them in the PyTorch Distributed backend. So first of all, we tested TCPStore, and I will show the result in the next slides. So basically, we added a non-blocking implementation for TCPStore called libuv, and in the test we see it scales to up to 32K ranks, which is a super large number. So that means temporarily we are safe on this thing. Like until 32K, you're okay. You'll be okay. And let's see that first. So here is the benchmark. So we see some lines. So this vertical lines means the old TCPStore is likely to fail at 8K. So this is the number, 8,000 GPUs or ranks. And with the libuv backend, we make it scale to 32K, which is the right end. And we see that the startup time is the same before 4K, but after between 4K and 8K, the libuv takes more time to start up. So this is because we add some randomized slowness to each client, so that they will not rush to the server at the same time, which is like a DDoS attack, right? So at 8K, the old TCPStore failed, and the libuv backend still works, and the time is linearly growing, which means it is still scalable. And another thing we test is the barrier. So in some cases, we still use the TCPStore to perform barrier to synchronize among the ranks. So this happens where the process group has not been initialized. And we see that this line is the execution time of barrier. It is even at 32K, one barrier just takes less than 1 second, around like 700 milliseconds. So that time is acceptable in most cases. So we can say that the TCPStore, the libuv version is okay for 32K. You don't need to worry about it. There are no issues. Yep. And the next thing is the Gloo. So what we do is we test this process group using Gloo backend on initialization, and we see that it scales to 8K, but not beyond. Yep.
I asked why it was limited to 32K.
You were sorry, what?
Why was it limited to 32K?
TCPStore or Gloo? Gloo is limited at 8K.
No, the
Yeah.
other one.
So TCPStore is we don't have more machines to perform benchmark. So I don't think in near future you will have that use case of more than 32K. So we didn't. Yeah, we just don't test. Yeah. But based on the trend, it should still scale. Okay, so then for Gloo, we see that the curve doesn't look good, right? It's not linearly growing. So we can see the number here. For 8K ranks, the total initialization takes more than 20 minutes, like 25 minutes. So it's like 1,500 seconds. So this number is okay for a job startup, because usually the job fails and it needs restart in a day or in like 20 hours. So like 20 minutes startup is okay for every like 20 hours. But what will be the case beyond? So we had tested on like 12K ranks. The number would be 1 hour for initialization. That is a long time already. Especially with more ranks involved, the time to fail for the job will be shorter, because you have more GPUs. You have a higher chance to fail on one of the devices. So the job cannot last for like 20 hours. It will be even shorter. And you will have 1 hour to restart the job. That is unacceptable. So in this sense, we think the current Gloo implementation does not scale beyond 8K. At 8K, it is okay. And we also have the breakdown. We see that the use of TCPStore takes the orange part, and the Gloo full mesh connect takes the yellow part, and they're mostly the same. So both are the bottlenecks. So we plan to optimize them, and we have some ideas on how to do that. So hopefully we will get to be able to scale beyond 8K. Yeah. So this should be able to happen in the next 3 months or 6 months. So the last thing is about observability. So this is a more urgent topic for us because this is about debugging. And we have seen this issue in many real jobs. It is super hard for user to debug in a 2K GPU job, because you have so many logs, just like Omkar has mentioned, right? The super large, the large logs. You may even need like LLM technique to help parse that. So the thing is, the current debugging tool in PyTorch Distributed is not suitable for this case. So currently, we have two things to help user to debug. One is called Nickel Watchdog, which will get the thread timeout if the collective is its hand there. If it doesn't proceed, and this will kill the main thread. And another thing is called nickel desync debug. So this happens. This feature will be used whenever a timeout happens. It will send a report to the TCP store, which is hosted on the first rank, so that you can find the report on that host, and that report should give you information about which rank joins the last collective, which one doesn't. So this is very useful because if you see one rank doesn't join the collective, we know that rank has some issue. You just go to that rank and see the log and figure out what happened. So this is very useful in our based on our past experience. However, this one doesn't work well with like 2K GPUs because of several limitations. So the first thing is when the watchdog kills the thread, right? Assume that it happens on rank 0, where the TCP store is hosted, and the thread is killed. And other ranks will try to send the report to that rank. However, the store is gone. So in that sense, the TCP store, the desync report will not help because the store is no longer there. You cannot see the report. So we add a PG hook to handle that thing. So basically, we separate that watchdog and desync report from one. We used to have them on one thread. We separate them to 2 threads, so that the timeout will not kill the TCP store thread. So in this case, we will have the report even if the main thread was killed. And also, this hook should be customizable so that our customers can register their own exception handler to PG. So whenever a collective failure happens, the custom handler will do the job to help user to debug. So this is a very useful tool, we think. So we get feedback from many customers. They all want this feature. Yeah. So I think we believe that with those techniques or features, we should be able to to make the error detection easier. So that we can figure out stragglers. Like for example, one rank joined the collective very late, and eventually it causes collective timeout. Or we can figure out like hangs or crashes on certain ranks. So this closes the talk. Any questions?
I had some of the slides that talk about how DeviceMesh is going to be an interface for 2D parallelism. Is that going to continue to expand into ND parallelism, or is the interface for something like that still being defined?
Yeah. So.
Can I steal one of your mics with the questions? Yeah. And just hop on next to the
Yeah. DeviceMesh is.
DeviceMesh?
Oh, okay. It's right here. Oh. Yeah. Oh yeah. So yeah, we're working on like this DeviceMesh support. So naturally, if you're seeing like the device mesh initialization, it can actually support to ND, right? So because you would have a 3D, you can still slice like your 1D device mesh out of it for 3D composition as well. So device, and we're gonna be moving device mesh to a standalone package for distributed. So it will be like this generic package for you to manage your device layout. Yeah.
Yeah. So what are some of the differences with the DTensor UX compared to what was done before? I know there are other sharded tensor implementations in PyTorch. So what was the reasoning behind the switch, and what are you guys sort of thinking for the future?
Yeah. I can talk about that. So when I first joined like a distributed team, we were still working on sharded tensor, but later on we found that there are some limitations around sharded tensor. For example, sharded tensor only can represent sharding, right? However, in the distributed world, sometimes you want to for example, for DDP essentially is just replicate, right? So we want so DTensor itself has like a multiple scenario like partial, replicate, and sharded tensor, and then originally, sharded tensor is even not a subclass of tensor, so that actually took us a lot of effort to eventually convert to a tensor subclass. And then we found that, like all these kind of things doesn't, like, we don't want to go down the wrong path for very long. And then we decide to redesign, and then we recreate the DTensor, and then we deprecate the shard tensor already. We send a warning message there. So I guess the recommendation here we have for our customer and for community is that just don't use shard tensor and then use DTensor. If you have any feature requirement or if you see any feature gap, just come to us, say, hey, okay, here's your requirement. Yeah.
And to add on that for a little bit, so like naturally, like sharded tensor, as Junjie says, is not aware of any replication, and it doesn't really support composable. So it's not aware of your global layout. But with DTensor, you can do 1D, 2D, and 3D, which naturally help checkpointing to be much easier. We actually have a prototype for 2D. 2D checkpointing with sharded tensor. It's really like a pain as we learn a lot from like we don't want to get into that UX hell, so we just want to switch to DTensor, which is like a better support for this. Yeah.
And also DTensor now has work with Torch compile already, right? So then you get the Torch compile benefit.
Wait, so sorry, one more quick follow-up.
Yeah, sure.
So what are you guys thinking about in terms of Torch compile and DTensor? Are you just going to, like, if I give you like a Torch module, will you just sort of figure out the best way to parallelize that, or is that sort of the vision?
I think the other way around, like you still like call like after you call TP.API and then wrap with FSTP and then you call Torch compile. Yeah. So that's the current thought around that. Yeah.
You mentioned somewhere on the slide that there's some PyTorch native parallelism work going on for inference. Can you elaborate?
We're still working on that. So currently, I mean, people have applied DTensor for tensor parallel in the inference, but I think we're still working on that. So yeah.
And I think there's a separate talk yesterday talking about this, and you can go back to the PyTorch conference schedule yesterday. I think they will be releasing the YouTube video soon.
Right. Horace and then Hamid, they were talking about like PyTorch inference.
Yeah.
Thank you very much, guys. Let's take